Hello and welcome to this acid-base reaction question, but we're going to make it a bit more challenging by using a slightly different alkali than normal, aluminium hydroxide, and also try and apply the ice method to this even though it's not technically in equilibrium. We're also going to bring in the idea of different temperatures and how they might affect the pH of the resulting solution. So the question is fairly straightforward. It gives us two reagents and the values for each to be able to work out the moles, and it asks us to work out the pH of the resulting solution. So the starting point is to write the balanced equation, and you can see that the mole ratio from 3 to 2 is slightly different to a normal acid to simple hydroxide mole ratio. So what I mean is, in normal A-level questions, you might have sulfuric acid to sodium hydroxide, which is 1 to 2. This time it's 3 to 2. So how did I come up with that? I used the salt that you make, the aluminium hydroxide. I constructed the formula of that from Al3 plus and SO42 minus, and to balance the charges I needed to do Al2 SO43. So working outwards from that allowed me to end up with 3 to 2 mole ratio on the reaction side. So then you can apply the ice method. So we're using the equation and putting initial and change as normal, but instead of equilibrium moles, we use end moles because, like we suggested already, it's a strong acid and strong base reaction, not a weak acid partial neutralization. So it wouldn't involve making a buffer. But the ice method is still, so let's have a look how we might do that. Let's start with our acid and work out the number of moles we had to start with. Do the same for the alkali, and you can see straight away that the alkali is in excess. So we put those into the initial row, and then the change can be worked out by subtracting the number of moles of acid from the number of moles of alkali, because the alkali is in excess, and that leaves us with 9 times 10 to the minus 3 moles of aluminium hydroxide. So it now becomes a kW calculation. So we can use the kW expression to proceed. So we assume that kW at this temperature is going to be 1 times 10 to the minus 14. We haven't been told it's hotter or colder than 298 Kelvin, so we can go with that assumption. So working out the concentration of aluminium hydroxide from the number of moles of it we've got, and the actual total volume, which is now 36.5 centimeters cubed, we get 0.24657,534. And multiplying the number of aluminium hydroxides by 3, because you have 3 hydroxide ions for every formula unit of aluminium hydroxide, we need to actually use 0.7397262. So if we do that and rearrange the kW expression, we get 1.35 times 10 to the minus 14 as the hydrogen ion concentration, which gives us a pH of 13.87. Now, think about what happens when kW is altered due to temperature. If we make it higher, then water will dissociate more, because, as you know, the breaking of the bonds in the water to dissociate it would be endothermic. So now, simply assuming that kW is 1 times 10 to the minus 14 is no longer applicable. So let's assume that we now have a slightly larger value of 1 times 10 to the minus 10. What would happen to our pH? We're going back to our number of moles at equilibrium. We use the kW expression to work out H+, but this time using 1 times 10 to the minus 10. So that gives us 1.35 times 10 to the minus 10, not 1.35 times 10 to the minus 14. So now, if we put that in, that gives us 9.87, which is a lower pH because more protons have been dissociated, because more water has been dissociated. Okay, hopefully this has been a useful look at how to do this type of question, how to construct a slightly more complex acid-base equation at the beginning, and also how you can use the ice method when changes of moles are happening. It doesn't necessarily have to be in equilibrium for it to apply. Okay, thanks for listening. Until next time, see you soon.